recording. Okay. Okay, so let's start. Thank you, Fiona, for joining us. Today, our speaker for the Astro Seminar is Dr. Fiona Panther from UWA. She obtained her PhD in ANU after doing her undergrad at Auckland. And after doing a postdoc in UNSW, she has moved to University of Western Australia, where she is working with OSGRAPH at the moment. Yeah, she is going to tell us about her work on rapid transients to nucleosynthesis. So please take it away, Fiona.
Thank you very much. Yeah, it's really nice. Nice to see everyone. It's really good to see people getting back together in person, which we've had for a while in Perth, and I know you guys have had it pretty rough over in Melbourne, so it's really good to see. Yeah, so I'll talk a bit today about this is not just the gap with regards to, going from observations of rapid transients to looking at microphysical processes, but also the gap between where I did my PhD. So I did my PhD looking at microphysical interactions of antimatter and where it comes from, especially in the Milky Way, to now looking at gravitational wave detection. So there's a bit of a gap in my career, I guess, jumping from one to the other, and this is how I see the bridging that gap. So I work at UWA. I'm part of the SPHERE online gravitational wave detection pipeline team, and part of OSGRAPH as well. So I'm interested in rapid transients, early warning of things like neutron star mergers. The background image here, this is from Ivo Zeitenzahl, who was my boss at UNSW. I just think it's a really beautiful supernova remnant. It's also very, very interesting. You've got this little torus down here that's kind of hiding, and there's a neutron star in the center of it, and what's actually created that torus, no one's really quite sure. So this is in the Large Magellanic Cloud. It's a beautiful supernova remnant. This image is from ESO, from Muse. So I'm going to talk about transients. So this is one of those diagrams that shows you the zoo of transients that we really observe now. So this is particularly with regard to optical transients, this diagram. So you've got the magnitude of these things on the y-axis, and then you've got the decay time. So how quickly the light curve declines over time on the x-axis. So there's a lot of different things populate this parameter space. Some of them may be things that you are interested in. I'm not leaving things out. I'm not really going to talk about long GRBs or really that much about short GRBs today. I think they're very interesting things, but it's not really what I focus my career on. I'm more interested in these things that they're not particularly bright, they're not super faint, so they're not as faint as, say, classical novae, which are actually hiding down here, but they are relatively faint things. So I'm particularly interested in, from my PhD and my first postdoc, things like type 1a supernovae, peculiar type 1a supernovae, which I'll tell you a bit about, and these things called calcium-rich gap transients. So these are all types of, we think, thermonuclear explosions that maybe don't look like what we think that thermonuclear explosions look like. We usually think of type 1a supernovae. I've also done some observations with luminous blue variables in the past, part of TOO campaigns with the ANU 2.3 meter telescope. And now I'm quite interested in kilonovae, and what happens before something becomes a kilonova, and also quite interested in these dot 1a objects, which are very faint, very fast decaying transients that may be type 1a like. So I'm generally interested in faint, fairly red, generally weird looking transients. So these are things which would usually be thrown out in cosmological analyses. They'd be considered junk, they'd be considered contaminants. But I'm quite interested in them because I think they tell us something really interesting about the gap between what we observe and the nucleosynthesis processes that take place. So it wouldn't be a talk that I give if I didn't show a Plato's cave analogy. So astrophysical transients, I think they're interesting because here you've got matter that's being pushed to some kind of physical extreme. You're either compressing things to extremely high densities You're putting stuff under immense pressure. You've got very high temperatures. You've got relativistic velocities. And this means as well that you can actually see a lot of these processes happen in real time, because when you've got these extreme processes taking place, they're going to be happening on human timescales. They're going to evolve over seconds to hours to days to months, something that we can really perceive, whereas something like star formation over cosmic time, not really something we can perceive. So I think, we tend to split ourselves into two sort of brackets in astronomy. We have the simulation side. So you've got your simulation. We look at our simulations with a series of assumptions, which are usually based on the microphysical processes that we are using to make those simulations, be it nucleosynthesis or radiative transfer or hydrodynamics. And those produce a whole bunch of synthetic observables. Maybe we're looking at synthetic light curves. We're looking at gravitational wave signals that could be seen by something like LIGO. And we, as theorists, tend to look at those synthetic observables and try and make some sort of reasonable interpretation. And so I've written quite a lot of papers that have this idea where you do a simulation, you make a few assumptions, what would we see? And then I point at that and go, yeah, that's what we would expect to see. Sometimes quite divorced from the observers. This is especially true, I've found, with type 1a supernovae. There's not usually a huge crossover between the observers who are doing cosmology and the people actually doing the simulations of the things. So the observers, they like to just look straight at stuff and we go, okay, well, we're observing reality. And then sometimes the reality and the synthetic observables, they don't really match up all that well. Actually, in practice, having done quite a bit of observation myself, this is actually what observing is like. Okay, so you've actually got some sort of reality. You're then going to observe that reality with an instrument. So you've got some sort of physics going on inside your instrument. I've worked with gamma ray detectors for a long time. So that's things like radioactive processes which produce signals in these telescopes. There's some instrument response and some background. Then we make that observation. So you're never actually directly looking at reality. You're looking at reality processed through a whole bunch of physics and assumptions about our instrument. What I like about multi-messenger astronomy is that this is one of these ways we can tie all these things together. So you can actually combine your observation and you can combine your theory together really nicely, because you've got all of these different parts of the observation that you can try and match up to different parts of the theory. And so that's one of the reasons why I kind of changed my career direction a bit. I got a little bit over the, the type 1a supernova, the theorists are over here and observers are over here, and never the twain shall meet. Whereas I found in the whole multi-messenger astronomy, when we're usually thinking of things like kilonovae, although this can apply to supernovae as well, everyone is really working together. And certainly in gravitational wave detection, we're having to focus on the predictions made by the theorists in order to actually do the searches. So as a matched filtering pipeline, we have to take those theories and then try and look for those signals which have been predicted in data. So I'm going to start really by talking more about thermonuclear supernovae. And then towards the end of my talk, I'm going to sort of circle back towards more of the multi-messenger gravitational wave side of things. So I spent most of my career thinking about thermonuclear supernovae. So these are usually classed as type 1a supernovae. People usually go, yep, these are standard candles. We use them to measure distances. Firstly, there are lots of different thermonuclear supernovae. There are actually more types of thermonuclear supernovae that we really know of than there are core collapse. And we only use the normal, or there's sometimes called branch normal type 1as as standardizable candles. So these things actually aren't intrinsically standard candles. You actually have to standardize them. So what you do is you say, okay, well, we notice if we look at this left-hand plot, you can see that the fainter supernovae, they tend to fade faster, and the brighter supernovae, they tend to fade slower. So intrinsically bright means slower decline. And there's actually a pretty tight relation between those two things, which is the Phillips relation. This is driven by the fact that there's more radioactive material produced in a brighter supernova. But this is purely empirical, so the standardization doesn't actually rely on any of the microphysics. It's just an empirical relation that kind of works. And so if you can correct these light curves for this stretch luminosity relation, and then you can actually get this standardized. You can then use them as standard candles. So they're standardizable candles. But this is only true for normal type 1a supernovae. Lots of supernovae that are thermonuclear will deviate from this rule. So the light curve is a basis for all of our physical understanding of what powers type 1a supernovae. And I've kind of given it away with that equals more radioactive stuff, because that's what's happening here. So this is a really fascinating thing, which has a really interesting bit of history behind it. So there's been a lot of theories for a long time, sort of since the early 1960s, that this light curve of type 1a supernovae is powered by the decay of nickel-56. So the decline of the light curve follows very sharply the exponential decay from, follows the Bateman equations for the decay of nickel-56 to cobalt-56. And then there's that kink that you can see in this plot that I'm showing here. And that kink in it is coming from where you now get the decay of the cobalt-56 to iron-56 taking over. At very, very late times, things are kind of powered by other isotopes and also by positron annihilation, but that's really after about 400, 500 days. So this theory usually gets attributed to Colgate and McKee. This is a 1969 paper that's very, very famous. And also there was a lot of work done on this by, I always forget the name, which is terrible. Oh, he was Evo supervisor as well, and his name has escaped me right now. Yeah, I've completely forgotten the name. That's not great. Oh well. So the main point I want to make, though, is that while this theory is generally cited as Colgate and McKee, it actually came from a man called Titus Pankey Jr. And he wrote his PhD thesis in 1962 at Howard University, which is a historically Black college in the United States. And Pankey, when he graduated, was one of only 10 Black physicists in the world. You can actually access his thesis online now. So there's been several of us who've been trying to draw attention to Pankey's work along with his family. He's a very interesting man, a very accomplished physicist. So this is a plot from his thesis where this was the first time this had really been done, where he's showing, the line is showing the decay of nickel-56 and then cobalt-56, along with the measurements there. It's all hand-drawn, but that's from Barty's supernova, which is a type 1a supernova. And so Pankey's work hasn't actually really had the recognition that it deserves. And one of the reasons for that, he died very, very young. He was actually attacked in his own home at one point, and he suffered a brain injury, and he died very, very young. He didn't die from his brain injury. He did work for several years following that. But I do want you to try and sort of, if you take one thing away from this talk, remember his name, because he's a very important part of the history of thermonuclear supernovae, and he was the very first person to suggest that it was nickel-56 that powers the light curve. Yeah, and do go and have a look at his thesis, because it's definitely worth taking a look at. So back in the 1960s, there's not all that many measurements of supernovae around, including type 1a supernovae. But as the years have gone on, we've had more and more supernova surveys. People really want to observe these transients, and the more surveys that we've had, the more problems we've had. And so what started out as kind of this very tight relation is a black line down the center of the plot there, which is the Phillips relation, which is this luminosity to decline rate relation, which is obeyed very, very strictly for normal type 1a supernovae. Around the early 90s, people started noticing that stuff deviated from this. The first was the 91b G-like supernovae, which is shown in red. So they kind of like drop off the bottom of the Phillips relation. So they're non-standardizable, but they are thermonuclear because they exhibit the same properties of the spectra that you would expect in thermonuclear supernovae. So no hydrogen, no helium, and quite a bit of silicon. You also have 91 T-like supernovae, also discovered in 1991, which tend to just occupy that very, very top end of the Phillips relation. They're that beige color. So they sort of pop off the top of the Phillips relation. And over the years, more and more of these peculiar type 1a thermonuclear supernovae have been discovered. So you've got everything from things which decline very, very fast. There's only a handful of those fast decliners. Then you've got things which are below the Phillips relation. So everything below is generally termed subluminous. And the subluminous supernovae, you have O2ES likes, 1AX, and then the calcium-rich gap transients, which get their name from being in that gap between the different types of 1AXs. And then at the top of the Phillips relation, you have type 1A supernovae that interact with circumstellar material, and also superchandra SN1A, which are ones where we think that the white dwarf that's exploded is larger than the Chandrasekhar mass. So you've got a huge amount of diversity in what people generally present as a relatively homogeneous population of supernovae. There's actually, yeah, as I've said, more diversity in the type 1A supernova population than there really is in the core collapse supernova population. There's also a lot more uncertainty when it comes to modeling these things. And so when you try and figure out what the progenitors are, there's a whole bunch of different theories. They generally revolve around the same thing. So every single type 1A supernova, in order to produce the nickel 56 that powers the light curve, you have to have at least one carbon-oxygen white dwarf star. That carbon-oxygen white dwarf star has to be around the Chandrasekhar limit, and then some sort of merger process or some accretion process is going to drive it over the Chandrasekhar limit, and then that will cause the explosion, which we see as this really nice bright transient. So the picture here is very, very famous, SM1994D. So if you want to show a picture of a canonical 1A, 1994D is basically the one that you show. It sticks out nice and bright against its background galaxy. So we can class the different progenitor models broadly into two different groups. Either you've got double degenerate, which means you've got two white dwarf stars, two stars made of degenerate material, one of which is composed of carbon-oxygen. The other can either be a carbon-oxygen white dwarf or a hybrid or a helium white dwarf. It's not necessarily true that you have to have two carbon-oxygen white dwarfs. These two things will eventually spiral closer and closer together by producing gravitational waves. And so this is the kind of signal that you can maybe detect as sort of the stochastic background with something like LISA, one of these space-based detectors. The other idea behind this, which was popular for a little while, was the idea of violent mergers. So the idea that these two things could have some dynamical process which causes them to collide quite violently. So this was a really nice paper by Rudiger Packmore from 2010. It's a really, really interesting idea. The other model, which I prefer the double degenerate models in general for most type 1A supernovae, but there is another camp which prefers the single degenerate model. So here you have your one carbon-oxygen white dwarf star, and it has a companion, which is usually a hydrogen or helium donor. So it's usually something kind of on the red giant branch, and it's going to go through something like common envelope or Roche-Lobe overflow, and it's eventually that mass will accrete onto the companion, and then the carbon-oxygen white dwarf will eventually explode. And it can explode slightly below the Chandrasekhar limit, which is a sub-Chandrasekhar model, or it can explode at the Chandrasekhar limit. So there's a lot of uncertainty when it comes to progenitors. There's probably some combination of these two processes which produce this population of transients. There's also a lot of uncertainty when it comes to explosions. So the explosions can be subsonic, deflagration, supersonic, which is a detonation, or they can transition from one to the other. So you can start subsonic and become supersonic. Both merger products could burn, which is a double detonation, or only one may burn, in which case you might be left behind with this companion star. The merger products may also have a layered structure before the explosion, and we also don't well understand where this explosion is initiated. And this actually has to be implemented manually in numerical models. They won't just explode on their own. You actually have to say, okay, ignite here. The other thing I want to point out is the Chandrasekhar limit usually gets quoted as 1.4 solar masses, which is sort of shorthand. The Chandrasekhar limit is not a mass limit. It's actually a density and temperature limit. And it's the density and temperature such that you get explosive burning of the carbon and oxygen to nickel 56. So it's just something to bear in mind. And that's why we can get these sub-Chandrasekhar models, because you can still somehow compress stuff enough that you can be less than 1.4 solar masses and still burn explosively. So one of the ways we can learn about progenitors is actually not by looking at the progenitors at all. What if you looked at the host galaxies and the stellar population that hosts the supernova? So this is something that I did with 91 BG-like supernovae, these subluminous peculiar type 1As. So different models, different progenitor models are predicted to have different lifetimes. So the delay time distribution, the time between star formation and explosion, means you can discriminate between models. And normal type 1a supernovae don't come from particularly old stellar populations. They have a peak delay time of about 1 gigayear, which is not very, very old. So if we look at the host stellar populations, and we don't see any old stars, and especially no A stars and no active star formation, it means we may have something coming from something with a much longer delay time, which means it may have quite a different progenitor from the normal type 1As. So these 91Bg-like supernovae, they're the largest subclass of thermonuclear supernovae. They have no hydrogen in their spectra, like thermonuclear supernovae, and strong silicon-2 absorption. So this spectrum that I'm showing here shows you in blue, this is a type 1a spectrum, and the red is a 91Bg spectrum. The offset is just arbitrary. It's just so I can fit them both on the same scale. So these are the largest subclass of peculiar type 1as. So they're 15% of all type 1as. But if you restrict that analysis just looking at early type galaxies, ellipticals, they're about 30%. And they're spectroscopically and photometrically peculiar. So they're subluminous, they fade very, very quickly, and they're not standardizable. And they have very strong titanium-2 absorption, which is that pink band down there. There are some hints at these things having very old progenitors. So most of these supernovae occur in early type galaxies, so ellipticals, that lack ongoing star formation. So this is showing here in this plot, this is a cumulative distribution function. So you find that the 91Bgs tend to be overrepresented in elliptical galaxies and much less so in spirals compared to the normal type 1a, so it's the blue line. There's also a suggestion that the rate of these things decreases at higher redshift. This comes from SNLS, paper by Gonzalez Gaetan in 2011. It would be interesting to do this measurement with the dark energy survey, although it's not yet been made, because that high redshift bin from SNLS is about redshift 0.1. There was only one event in that bin. So it would be good to see that measurement made with better statistics. And so with these hints at old progenitors, I actually went away and did some work during my PhD to try and figure out what's going on. And so what I did here was I decided, well, what if I look at the host galaxies? But I won't just look at the host galaxies. What if I look at the stellar population within a few kiloparsecs of where the supernova exploded? So I used this wide field IFU. It's on the ANU 2.3 meter telescope. It's the wide field spectrograph, or WIPES. It's like a mini MUSE, like on the VLT, a very small version of that. So it's got a relatively large aperture, which you center on where the supernova exploded. Supernovae have long since faded. We only care about the galaxy spectrum. We're not looking at the supernova. And we want to look at the properties of the population within a few kiloparsecs of the supernova. So we spectroscopically select those supernovae. They come from the BSMIP sample, which is Jeff Silverman's work from 2012. It's classical observing. This is just for the observing nuts. This was a really good 14 nights of my life. Actually, it was a really interesting campaign. And in the final sample, we have 12 spectra, which are we extract spectra from a seeing limited aperture, 3 arc seconds by 3 arc seconds, centered on the supernova location. So the very, very center of that little square. So we're looking at sort of on the order of several kiloparsecs around the supernova. And this is what we saw. So these are 2 different examples of galaxy spectra out of the sample. And so this was fit using PPXF, which is Michele Capillari's software. And so the black line that you can see is the actual observation. You can see that the top one, this is from 2000 EJ. This was a very, very old stellar population. There's no real evidence of young or active star formation. And on the right-hand side, this is just a plot showing the mass fraction of stars in that population that are in different age bins and metallicity bins. So that top one, you've got relatively high metallicity and very old stars. The bottom spectrum was a bit interesting because this was actually a spiral galaxy. It was edge-on, which means that I think the supernova, based on where it was located, blew up in the bulge, which would be an old stellar population. But we were looking through the disk. And so you see this star formation coming from the disk of that galaxy, which means this gets biased to a younger stellar population. But you see there are actually some greater than sort of 4 or 5 billion-year-old stars present in that. And so if you take the averages and draw some really nice big error bars, there is a question, but my mouse has disappeared.
Oh, sorry. I was just curious what the line around 5400 angstrom was.
It's a great big dirty skyline that I couldn't remove. I tried, but it's just a skyline. We basically exclude that from the fitting. But yeah, it's not great. But it's just one of those things you can't get rid of on that telescope. Yeah, so hopefully that explains what that's doing.
Thanks.
So if you actually look at some averages, so these error bars are just calculated by essentially marginalizing over those two different parameters, you actually find that these things tend to concentrate in older stellar populations. So the blue ones in the background, those blue points, are actually the same measurement but done for normal type 1a supernovae. And there's a very wide distribution of stellar population ages for the normal type 1a supernovae, whereas the 91Bg-likes seem to concentrate in the older stellar populations. The youngest population there, that kind of outlier, that was a galaxy that was at about redshift of 0.1. I think it was 0.1, and that was completely unresolved. And so you're seeing the whole galaxy in that aperture, whereas most of the others were looking at a region which was only sort of 2 to 3 kiloparsecs in size. So you can have a look through the paper to see the actual sizes. But what we determined from this, that these are probably coming from the oldest type of progenitor known for any supernovae, progenitors that are going to be older than 4 to 5 billion years. And this is in line with a lot of the population synthesis modeling that we've done on these supernovae for a separate paper. So we'd kind of been hoping for this result, and it really did confirm some of the population synthesis modeling for the progenitors that was done by Ashley Reiter for another paper. So that's one way of looking at what the progenitors of different transients are. And that's the kind of measurement that can also be done for things like kilonovae. It can be done for FRBs. It can be done for other supernovae. I want to move on to something a little bit more direct that requires prompt follow-up. And that's actually gamma rays directly from supernovae at prompt times. So as I've said, there's possibly less known about the progenitors of type 1As than there is core collapse supernovae. We have no pre-explosion imaging of the progenitors of these things at this point. They require binary evolution, although so do core collapse supernovae, but there's a lot of uncertainty in the formation channels for these things. And there's also no self-consistent model from formation to explosion. So you have to go from population synthesis, you get your final configuration, you then do hydrosims of the pre and post explosion, you then have to hand implement where your burning initiates, you then have to then take that to a nucleosynthesis network, then you have to post-process that to get your synthetic observables. So we have these two models. We have many different models for how these things explode. But until 2014, we actually didn't even know for sure that nickel 56 was powering the light curve. It was conjecture. It was a relatively good conjecture. There was a lot of circumstantial evidence, but no hard proof. So that's because generally when we look at spectroscopic observations, we look in the optical, maybe the infrared, maybe the UV. And these spectra come from the electronic structure of the atoms in the supernova ejector. It's very hard to probe nucleosynthesis with this because atomic spectra are insensitive to isotopic composition. And isotopic composition is very, very important if you want to know what sort of nucleosynthesis is happening. So if you look at line emission from a remnant like Cas-A, this is a core collapse supernova, but it kind of serves for the point. That's looking at some emission in the gamma ray from very long-lived isotopes. So something like titanium-44. So in Cas-A, if you looked at the optical spectrum, you'd maybe see some sort of absorption trough, which is coming from titanium-2 at relatively late times, maybe even promptly, but you can't be sure whether it's titanium-44 or another isotope. So you don't know where on the nuclear statistical equilibrium curve you're actually sitting when you're making the titanium. However, if you look in the gamma rays and you see that lines from the titanium-44 decay, and these are some measurements, the different fluxes over many, many years that have been made of the titanium-44 decay lines in the gamma ray with gamma ray telescopes, you can then convert that into the mass of that single isotope generated in the explosion. Whereas if you do that in the optical, you only know there was some titanium, but not which isotope. And so looking at gamma rays in supernovae kind of has a history almost as long as gamma ray astronomy. So the first direct detection of gamma rays from a supernova was a core collapse supernova. It was 1987A, got a little star there because this was a core collapse. And that was actually from cobalt 57, which powers the light curve at very late times, greater than 8,000 days. Moving on into the 90s, there was then a few claims of detection of nickel 56 in 1991T. This was a peculiar type 1A, but those have largely been contested. They were very, very low significance, probably nothing there. 2011 FE was relatively nearby. It was within 10 megaparsecs. And there were some limits made on the nickel 56 emission, nickel 56 gamma ray lines, but it wasn't until 2014 where there was a direct detection of prompt emission of gamma ray lines from supernova. And this actually confirmed for the first time, absolutely with no doubt, type 1A supernovae are powered by nickel 56. So the little spot there in the crosshairs, that's 2014J. It was about 4 megaparsecs away. So it was nice and close in cosmological terms. So what about other isotopes? Well, understanding isotopic composition actually helps us understand the progenitors. The nucleostatistical equilibrium that drives nucleosynthesis is sensitive to temperature, pressure, density, and what's actually in the burning material. So you can bias your statistical equilibrium to producing different isotopes and different amounts of different isotopes. And helium burning is actually a really interesting case. There are quite a few type 1A progenitor models that involve some degree of helium burning. So you've got some helium layer present, and then you get some sort of alpha capture process going on. And the ashes of these helium burning type 1As is that they're overabundant in alpha isotopes. So things like argon 56, calcium 40, titanium 44, chromium 48, and iron 52. And I've highlighted chromium 48 because this is a really interesting one. Turns out you can't really detect the chromium emission lines, but the vanadium, on the other hand, you can. So in the most recent paper I've put out, I'm actually showing that you can use observations of vanadium 48 emission in the sort of 5 to 30 days post-explosion as a robust observational signature of helium detonations in thermonuclear supernovae. And so that plot that I'm showing here, the gray bars, they're showing where the vanadium emission lines are in a particular canonical model that we use for these helium detonations. And these are actually quite detectable very nearby with current telescopes, but even more detectable if we look towards future telescopes. So if you look at a light curve just purely in those two emission lines, so the red is the higher energy vanadium emission line, the black there is the lower energy vanadium emission line. So this is just the vanadium line, which is contributing to this gamma ray light curve. What we do is we can calculate the maximum distance where you could see one of these events at 3 sigma with different gamma ray telescopes. So we use a 1 or a 1.5 megasecond exposure. I can explain why that is a bit later on. I'm not going to labor the point, just to say that that's optimal. And this light curve here is a canonical distance of 1 megaparsec. So basically what we do here is we say, what's the 3 sigma limit for these telescopes? Okay, how far away can you move this supernova and then still detect it at 3 sigma? And so for a telescope like Integral, you've got to be relatively close by, only 2.3 megaparsecs. So it's got to go off in the local neighborhood. Turns out the further in the future your telescope is, the harder it is to get an actual picture of the thing. So I had to crop this off the COSI website. But COSI is a future telescope that's planned to be launched within the next sort of 10 years or so. It's actually a balloon-borne detector at the moment. Done some really, really interesting work on diffuse emission. And the maximum distance you get there for detecting this kind of supernova would be 3 to 4 megaparsecs. And if you look even further to the future, this AMIGO detector, or All-Sky Medium Energy Gamma Ray Observatory, the maximum distance where you can see these supernovae is getting to 6 to 7 megaparsecs. Okay, so we've got some distances, but what's the actual chance that we're going to see one of these? Well, we need to calculate the rate from something. So we calculate the rate from theoretical models of how these things form. So this modeling was done by Ashley Reiter using Star Trek. And I'm showing here, this is the most dominant formation channel for these things. So you've got 2 stars, one of which evolves into a red giant, and you get stable Roche-Loeb overflow from that primary star, which is a red giant, onto the main sequence secondary. Then you get unstable mass transfer, you get a common envelope phase where that second star evolves into a red giant, and that first star has evolved into a carbon-oxygen white dwarf. Another stage of stable Roche-Lobe overflow, this time from the secondary, which is burning helium at this point, onto the carbon-oxygen white dwarf, and then you're finally left with a hybrid white dwarf and a carbon-oxygen white dwarf. And these two things have a period of unstable mass transfer where we assume that they merge. So Ashley was the one who did this modeling. Basically went and looked for all progenitor channels where you were left with a carbon-oxygen white dwarf with a mass of less than 0.55 solar masses. And the main progenitor that went into the model that was exploded for this study was something with a core mass of 0.45 solar masses in the CO core and a very thick helium shell. You've got 0.21 solar masses of helium. And so what we found is that basically the horizontal line there is showing where you've got a 10% chance of observing these per a 10-year mission. And we found that for something like Amigo, you maybe have like a 2 to 5% chance of observing one of these supernovae, observing these lines and confirming that there is some sort of process involving helium detonation across the extended lifetime of that mission. So it's not a very high rate, but it would be really, really significant because then you've got solid convincing evidence of a helium detonation. And so then you can start discriminating between different progenitor models. You can start saying, oh, well, there has to be some sort of helium donor involved in order to produce this supernova. It's also evidence that the bolometric light curve, so all the light added together, can be powered by decay of the light ion peak elements. So something like chromium-48 is actually powering the optical light curve of these things. You can look at Stuart Sims' 2012 paper where they actually show this in more detail with all of the synthetic observables. I just look at the gamma rays. And we also in this paper put some limits on the mass of vanadium-48 produced in supernova 2014J. And we find that there had to be less than 0.1 of a solar mass of chromium-48, vanadium-48 on the surface. We can't quite rule out the helium torus that was proposed for that produced this explosion in DL 2014. But if we had something like COSI or Amigo, we could have. And so we could have actually discriminated between different proposed explosion models for that supernova that was very, very nearby. So gamma rays, they're a direct probe of nucleosynthesis. You can see exactly what's going on. Another example that I'm actually quite interested in would be our process in either supernovae. I don't have spectra for supernovae. I would love to see them, or kilonovae. So kilonovae, I do have spectra, and that's what's being shown here. These are from Lee 2019. This is at 3 days post-merger. And then the different lines, so the bright green line that's very, very large, that's assuming this thing is at 5 megaparsecs. And so this would be detectable with, if it was at 5 megaparsecs, something like Integral, Amigo, or COSI. And we actually have a targeted opportunity for Integral for looking for kilonovae, where we would actually go after this big R process bump in the gamma ray spectra. I would love to see if we could also put something in for this about supernovae in the coming years, because I know that there are people doing the modeling of these supernovae which also produce gravitational waves. And if you've got a gravitational wave alert and you can localize that thing, then you can then go looking in the gamma ray for the R process. So you're not looking at the gamma ray burst, you're looking at the emission that comes from the very, very early stage of the kilonova where some of those gamma rays leak out. And these down here, these are some of the isotopes that you'd look for. Things like silver, bismuth, vanadium actually in there, interestingly. Cesium, promethium. So there's another question, if I can just find that. How good is the energy resolution of gamma ray burst detectors? Gamma ray burst detectors, you won't be able to do spectra. You can only really do counts in a very, very broad band. So you'd have to have a spectroscopic instrument, something like Integral SPI, maybe EBIS, and then in the future, something like COSI or Amigo, where you've got spectral capabilities. The gamma ray burst monitors just monitor a massive energy band, so there's no resolution.
Got it. And how good does it become for these future detectors?
So for the future detectors, so at the moment, the future detectors will actually have worse spectral resolution than integral. And that's just because you're going from a germanium detector to back to a Compton telescope. SPI is about 2 keV, and the future detectors will be about 10% at 1 MeV. And so you've got slightly worse spectral resolution, but on the other hand, you've got greater sensitivity. And for a very broad line like the R process, you actually want slightly worse sensitivity. It actually produces a better significance observation in the end, which I can explain at the end if people are interested. Hope that makes sense.
Right, but I mean, even if I look at the sort of the list of the lines here, right, you know, but at the 10% level, you know, some of these are going to be confused for each other, right? So that's
how
much of a concern is that?
That's the point. So what we wouldn't be looking for individual lines. We'd be looking at the sort of morphology of this big bump in the spectrum that I'm showing here from Lee in the top right-hand corner. And so that big bump is the contribution of all of these lines, and the different sort of morphology of that line, even on the sort of 2 keV level, you can kind of see and discriminate slightly between different models. So you're not looking for single lines. Yeah, cool. So I want to finish up by kind of spruiking where I'm going from here. So I've really been talking about timescales that are on the sort of days to months to years post-explosion. Of course, explosive transients, this isn't the only timescale that we'd be interested in. So I've been over here in the months to years kind of area with the supernovae. You don't need to get up in the middle of the night to worry about your supernova. It's still going to be there in the morning. It's not going anywhere. However, with things like neutron star mergers, which produce kilonovae, we know, and may produce other things as well, you kind of have to be there and you have to be ready to respond. So in 2004, we're looking at being able to produce early warning alerts. So basically saying, okay, here's a minute early warning that you've got a merger of 2 neutron stars. Get ready to look for the optical and gamma ray burst and the radio waves that could come from it. And so relative to these neutron star mergers, you're looking for different types of emission on different timescales. Could these be connected to fast radio bursts? There are some models that suggest maybe. So maybe you see an FRB 24 hours before the neutron star merger or several hours afterwards. Anywhere in that time window, there are models that could explain it. Immediately following, you've got your short GRB. You've got the possibility of X-ray and radio afterglows, which will then, you know, you go on and then you get your kilonovae and your very long-lived radio afterglow following it. And so one of the things that I'm interested in is this sort of area here. So working with SPEAR and in LIGO, together with MWA and SWIFT, we're looking at early warning follow-up of these gravitational wave neutron star mergers. And so one of the ways to do that is by using the pipelines, and my pipeline that I'm working on is SPEAR. So this is Lin Ching Wen is the PI of this. We've got a pretty good team here at UWA and also at Swinburne. So SPEAR stands for Summed Parallel Infinite Impulse Response. Don't worry too much about what that means. I'll explain it. We're one of the 5 real-time LVK pipelines. So there are 4 matched filtering pipelines, which is, we are one of them, and then 1 burst search. So what we do is we basically say, okay, well, here's our lovely numerical relativity waveform. Let's try and simplify that down as much as we can. So what we do is we approximate it using a series of damped sinusoids. And when you add those all up together, you sum them, you approximate the waveform very, very accurately. So you've got very high overlap between the summed filters and then the waveform itself. And each of those individual sinusoids get distributed onto single pole IIR filters, each on a GPU thread, and then you search for them in real time. If you find some, then you get these triggers out, and then you can do coherent candidate selection. So you basically make sure that your SNR peaks in each detector are time coincident. So you've got the right time delay from detector to detector. So for H and L, that's 10 milliseconds. HV, LV is 30 milliseconds. And we also are the only model search to do coherent search. So we check as well that the sky localization of these different triggers is also consistent. So this is explained in Chi-Chi's paper, which came out last year, which we're just revising now to be resubmitted. And this is all aided by GPUs. And so what we're now able to do is actually to do early warning. And so what you do is you chop up the templates and you cut them off early, you truncate them at an earlier time. And so there was a mock data challenge in the LVC low latency group in June 2020. And we managed to produce a mock GCN, so a mock alert, that came out about 30 seconds before the merger for this particular event. Obviously, it was a retraction because this is just a mock GCN. And so now we're producing alerts for neutron star mergers anywhere up to 70 seconds before merger. And so if you look at how the latency is different in this particular bit of work, this early warning experiment versus all of the previous alerts, you can now see that we're moving right down into the negative latencies. And so these early warnings are a pretty amazing opportunity. How many do you expect? Good question. At minus 10 seconds, we're maybe expecting 1 to 2 over the course of 04. So these two curves, they come from the different LVC rates for the neutron star mergers. And so 1 to 2 per year at minus 10 seconds. What about sky localization? Well, we would expect sort of for 10% of events at minus 10 seconds, 10% of the events would be coming out at about 100 square degrees. Okay, so that's still a very large area, but you've got 10 seconds before merger. So how can you improve the localization? One of the ways to do it is with the very prompt follow-up. And so you're working with telescopes that have very, very low latencies themselves and very, very large fields of view. So the prompt emission from neutron star merge is expected in radio, X-ray, and gamma ray. So one of the first ones that we would think to use, especially if something's in the southern hemisphere, would be to look with MWA. MWA has an all sky mode where basically you just look at the whole sky, and this can respond within 15 seconds of getting that early warning alert, which is very, very quick. And so you're looking for maybe radio precursor or very prompt radio emission, maybe even connection with FRBs. The other possibilities with Swift, there's a new pipeline which is made by Aaron Tohu at University of Toronto, and we're actually planning an experiment in the next couple of months to really see what we can do with Swift. Swift has a very large field of view again, and this is a really big possibility to use this sub-threshold trigger system to aid with the localization. There's also ASCAP in Fly's Eye mode, has a very large field of view, again, searching for radio precursors, and then Fermi and Integral together. Depending on which instrument, you've basically got a field of view, which is the whole sky, except for the bit that's occulted by Earth. And by combining all of these things together, you can maybe knock down that localization into the 10s or even lower square degrees. So there's some really exciting possibilities coming up with early warning. And moving from looking at transients on the sort of the evolution in the days to weeks to months to years timescale to looking really around what's going on during the merger. So if we can do this sort of science, if we can make these sort of measurements, we're then beginning to probe in real time the relativistic physics which is taking place in the merger. So just to summarize, transient astronomy is really special because it's allowing us to see some of the most extreme astrophysical processes in real time. And there are some really interesting opportunities, I think, to unify modeling and observations. So the observations will inform modeling, but also modeling informs, and in the case of gravitational waves, things like numerical relativity facilitate the observations themselves. So you've got to have something to compare, and you've got to compare it in a robust way. And so if you can have a good model that's principled, it's based on physics, we can test that with observations. There are also way more ways to figure stuff out than just optical photometry and optical spectra. I've shown the example of using host galaxies to look at delay time distributions and possible progenitors, gamma ray spectra to probe nucleosynthesis, and also gravitational waves. And these sort of things, they actually work for more than just the examples I've shown. You can do host galaxy studies of FRBs now. You can do host galaxy studies of potentially in the future kilonovae. And it's more than just looking at the average properties for the whole galaxy. What if you look at the very, very local region around where the explosion takes place? There's some interesting possibilities there. I think there's loads of opportunities for collaboration. 04 is coming, and so are the early warning alerts. This is going to be completely different from anything that has been done before. The idea that we could get advanced warning of a neutron star merger is just crazy and really, really exciting. I've got an O4 wish list. I don't know about you. My wish list, I still want to know what FRBs are. I want to know if neutron star mergers make precursor emissions. So do you get radio and X-ray precursors from these things? Can we follow up these early warning triggers with things like MWA and SWIFT? What about neutron star black hole mergers? Do they make electromagnetic emission? And can we directly observe our process nucleosynthesis with something really nearby? What is the neutron star merger rate? I think that uncertainty there is really, really interesting. Also, I always have on my wish list a galactic supernovae, and I tell everyone this because I'm sure if I tell somebody one day, someone will hear and make it happen. I just want to point out that I'd love to work with more people in Ozgrav and beyond. You know, if you have theoretical gamma ray spectra and want to know what an observation would look like, come talk to me. Even if it's like a byproduct of your simulations, you use it for radiative transfer. Well, maybe we can use it to see what we could see through any particular gamma ray telescope. Do you want to actually have observational gamma ray spectra of something? Depending on what it is, I can facilitate getting that. And also gravitational waveforms that can be truncated pre-merger. So if you're predicting waveforms that can be truncated 5, 10, 15 seconds pre-merger, maybe we can search for those using matched filter. So I'm really happy to answer questions. Yeah, and yeah, feel free to contact me at any point if you're interested. So thanks.
Thank you very much, Fiona. I hope you heard our round of applause. You can see it in the virtual claps. Yeah, so thank you very much for a fantastic talk. Does anyone have any questions? If you do, please raise your hand or write in the chat box. So meanwhile, if I may ask some questions. So you're looking at vanadium or vanadium, I don't know how to pronounce it. Yeah, so but you, in the nucleosynthesis, you showed it comes from chromium. So that you need some sort of beta decay to turn it into vanadium first and then get the gamma rays. So what's the timescale of that beta decay?
Yes, so chromium is very, very short-lived. It's got a half-life, I think the half-life is on the order of hours to days. So that's why you don't see the chromium, basically, because it's all gone from the ejector by the time you turn to look. The vanadium, on the other hand, has a half-life of, I think it's around about, the lifetime of the half-life is about 7 days. And so you see the lines come up over several days and then fade away. So you have a little bit more time to look for the vanadium. It's also in a really like optimal energy range in terms of searching. So you just get that bit more time.
Okay, thank you. So it might be a bit too long to be able to see neutrinos from the beta decays?
I think this is one of those cases. I mean, if these things blew up like right next door, like in our galaxy, I think that's a possibility. I'm not sure that. I'm actually not sure about the neutrinos. I only really know about the neutrino emission from 87A, which was really coming from like the core. Whereas with the type 1A supernovae, I'm not sure. I don't actually know what's been done around looking for neutrinos. My guess would be no, as I don't think there would be enough. It would have to be like in the galaxy to look and to see the energy spectrum of the things.
For the next, for the future neutrino detectors, there's some, prospects of seeing pre-supernova neutrinos. It also has to be in the galaxy, but you can see the neutrinos that come from a stellar evolution before the supernova. So if
that's cool.
Hyper-K has enough sensitivity for that, I mean, I thought maybe we can start seeing thermonuclear ones, but that's just
I think that's definitely a possibility. I might actually have a bit of a look into that. That sounds cool. Thanks.
Thank you. Any other questions for Fiona? I think you explained too clearly for everyone.
Or not clearly enough.
Can you hear me, right?
Oh, yep.
Yep. Great talk. Thanks, Fiona. I was curious. It sounds very exciting, this prospect of detecting these line features from supernovae. Is that capability part of the sort of design goals for these future missions you mentioned, or is there some prospect of improving the chances or anything like that?
That's a really good question. There's been a lot of discussion about these future missions, obviously. Usually the design goals usually involve positron annihilation from events. They now involve neutron star mergers, but usually when people talk about gamma ray lines, they talk about diffuse emission. And so this is something that I've really been pushing along with Thomas Ziegert to try and incorporate more of these kind of goals, because I think they're actually quite significant. It's certainly the nucleosynthesis, not specifically the vanadium, but there are the nickel 56, cobalt 57, nickel 57 are part of AMIGO long-term goals. And that's one of the reasons I wrote this paper, just because I think it's a nice non-core collapse supernova, unusual isotope to go looking for that has a bit of a relevance to theory.
Terrific, thanks.
Okay. Any more questions? If not, so we've almost approached our hour, so let's thank Fiona again. And yeah, thank you very much for joining us. And I'm sure, yeah, she'll be open to accepting any more questions over email or in person if one is open.
Yeah, thank you very much for having me. It's good to see everyone.
Thank you. And yeah, for the next week's, we have not a colloquium next week, but we have a screening of this film called Picture a Scientist, which is about women in STEM. So if you're around, please join us on Wednesday next week. Thank you for joining, and see you all.